just want to say good evening to everybody and tell you what fun it is to be able to introduce Professor Kirshner, Bob, as I know him, because he's a neighbor and friend, and he very graciously accepted this opportunity to talk to everyone tonight. And it makes me very proud to call him a friend. And I know he's probably going to hate me for this, but he has such an extensive bio, and I really do want you all to share the important pieces of it because he's done some wonderful things, and I'm going to share. He, first of all, is the Chief Program Officer for Science for the Gordon and Betty Moore Foundation, and also the Clues Research Professor of Science at Harvard University. A graduate of Harvard College, Bob received his Ph.D. in astronomy at Caltech. He did his postdoc work at Kitt Peak National Observatory and served on the faculty at the University of Michigan for 9 years before moving to Harvard, where he became the Clues Professor of Science. I'm overwhelmed, aren't you? He served as chairman of the Harvard Department of Astronomy from 1990 to 97, then as head of the Optical and Infrared Division of the Harvard Smithsonian Center for Astrophysics from 1997 to 2003. At last count, he co-authored 361 refereed papers that have been cited almost 52,000 times. All of this work has led to many prizes, including the 2014 Breakthrough Prize for the High Z Supernova Team, the 2015 Wolf Prize in Physics, which I'm going to get back to, and the 2011 Nobel Prize in Physics for 2 of his graduate students. Dr. Kirshner is the author of The Extravagant Universe, Exploding Stars, Dark Energy, and Accelerating Cosmos, which I understand even I will be able to understand. He was elected to the National Academy of Sciences, to the American Philosophical Society, and other learned societies. He served as president of the American Astronomical Society from 2003 to 5. In 2014, he received the James Craig Watson Medal of the National Academy for outstanding contributions to the science of astronomy. Robert joined the Moore Foundation in 2015 after 31 years as an astronomer on the faculty at Harvard. In addition to his work leading the science program at the Moore Foundation to accelerate progress in science, yay, we love that at ARCS, he continues his research into the nature of the dark energy that is accelerating the universe. And I mentioned the Wolf Prize because I noticed when I looked up the prize that when he was given the prize, he was lauded for, quote, creating the group, environment, and directions that allowed his graduate students and postdoctoral fellows to uncover the acceleration in the expansion of the universe. In other words, he really created the environment that allowed his graduate students to thrive. And of course, we at ARCS hope that each of the thousands of scholars that we've supported in STEM over the years will certainly have been able and are able today to have the same kind of environment and direction from their professors that Bob has given. So we miss you here in California, Bob. He's in Maine. You can just see that beautiful landscape behind him. Oh my goodness. We wish we had that landscape here in California because we're kind of droughty here. But say hi to Jane, and we welcome you tonight. And thank you very, very much for being our honored speaker.
Well, thank you, Linda. That was extremely nice. In fact, it was so good, I can hardly wait to hear myself. Let me share my screen, and who knows what will happen next. Here we go. Share. How's that? Can you see that? Yes. All right. So I'm going to talk about the transition from working on measuring the acceleration of the expansion of the universe to this somewhat different but not totally unrelated issue of helping to accelerate science, which I know that all of you at ARCS are deeply devoted to. So I have also made a transition from the Clues professor at Harvard to the chief program officer for science at the Moore Foundation, and I'll say more about that as we go along. Now, there is a way to do this. There is a way to do this. Here we go, there. Well, one of the big questions, of course, is what is the world made of? And here's a kind of representation of an old scheme. Air, I guess that's the empty glass that doesn't have the black magic shimmering cocktail. Earth, something's going. Fire, oh, maybe that's the black magic shimmering cocktail, and water. But honestly, the most important thing in this illustration is not the things you see, but the blackness around it. That is, I'm going to talk mostly about the idea that the things that you see are a very small part of the universe. Most of the universe is invisible. It's either the dark matter, which I'll talk about briefly, or the dark energy, which is the thing that we think is making the universe expand faster and faster. So let me say, I'll say more about that. Okay, so 100 years ago or so, people had an idea of where we were, and that we lived in a galaxy, the Milky Way, we call it. And you can see it across the summer sky in the north, and in the south, you can see some of these fuzzy things. These are the Magellanic Clouds that Magellan saw on his trip around the world. But, you know, the most important part of this story is that kind of inconspicuous thing over there. And the question was, in 1915, what was that? Was it part of the Milky Way galaxy, or was it something else? And I'll show you that the discovery that that was something else was the discovery that we live in a big universe made up not so much of stars, but of galaxies. And then later I'll show you that the galaxies are really showing you where the dark matter is. And by tracing the galaxies and their expansion, you can get evidence for the dark energy. So here's a demure woman who worked at the Harvard College Observatory, Henrietta Swan Leavitt. And she looked at those two fuzzy things I pointed out a minute ago, the Magellanic Clouds, and she thought, well, they're all at the same, all the stars in those things are at the same distance. And she noticed, or she said, it is worthy of notice that the brighter variables have the longer periods. This was a particular kind of vibrating star, Cepheid variable star, we call it now. And she noticed that you could tell which were the bright ones and which were the dim ones by measuring how long it took them to vibrate. So like a big bell vibrates kind of slowly and makes a low note. The big stars, the brighter ones, have the longer periods. Well, that was interesting. But it turned out this was the key to opening up our understanding of what the universe is. Well, here's Albert Einstein. Everybody knows Albert Einstein. Henrietta Leavitt, you know, she needs a better press agent, but here he is. And here's a photograph taken of Einstein at a scientific meeting. And you can see that the technology has changed quite a bit since then. This is an old kind of photograph. This person clearly left during the time of the photograph. This person was shaking his head. But the new change in technology is that now you can tell what people were thinking. And Einstein was thinking that the universe as a whole must be static, not expanding, not contracting. And the reason he thought that was that astronomers told him, or what he knew of astronomy told him, that the universe was the stars had small velocities, he saw from his equations of gravity, general relativity, the new gravity, that he needed to put something in there to make that happen. And he did. He put in this thing that is the Greek letter lambda, which we call the cosmological constant. And he said, I'm translating from the German here, that term is necessary only for the purpose of making possible a static distribution of matter as required by the fact of the small velocities of the stars. So he thought, okay, we live in a universe, it's static, it's eternal, and I'd better put a term into my equations so that they make that true. But, you know, science is interesting. You can have a really good theoretical idea, but, you know, you have to test it against the evidence. And people were gathering evidence about the motion of stars and galaxies, as I'll talk about in a minute. And here's one of the pioneers of that, a guy named Vesto Melvin Schleifer, working at the Lowell Observatory in Arizona. And this gadget is a device to take spectra, to take the light from stars and spread it out into a rainbow, and which he used to measure the speed at which galaxies were moving. And it's a little like looking at a highway, where if cars are coming toward you, the light would be shifted to the blue, and if cars are going away from you, shifted to the red. Well, of course, I mean, it's true when you look at cars going away from you, the taillights are red, but it's not that effect. But if the speed of light were 1,000,000 times lower, highways would look like this for that reason. So you can tell whether something's coming toward you or away from you. And the amazing thing that Schleifer found was that most of the fuzzy things, the nebulae, like the one I circled in that earlier picture, are moving away from us. Well, all right. Schleifer, you saw that telescope. It was pretty small, and he was working hard, leaning on it. Here is the really breakthrough instrument, which is the 100-inch telescope at Mount Wilson, which is above the little village of Los Angeles in California. Well, it was then. And the most important thing, again, is kind of inconspicuous. This is the place where the observer sits on that bentwood chair. And here is Edwin Hubble in that chair, photographed by Margaret Burke White, by the way, making some observations to try to see what the story was with those nebulae that people were worried about. Were they part of the Milky Way galaxy or something else? And here's a very famous picture that he took with that telescope on October 6, 1913. And he was looking for new stars, novae, and he found one. And then up here, he saw a new star, but then he realized that when he looked at some of the pictures he'd taken in earlier months, it was the same place. It was a variable star. And in fact, it was one of the kind of stars that Henrietta Leavitt had studied. And by measuring how long it took to go up and down, you could see whether it was a bright one or a dim one. And when you compared it to the ones that Henrietta Leavitt had worked on, he learned something really astonishing, which is that this fuzzy thing, the Andromeda Galaxy, which you can see in a fall night through binoculars or a small telescope, is not part of the Milky Way galaxy. It's too far away. Instead of being a distance, well, light travels about a foot in a nanosecond, so a billionth of a second. So you never see the world the way it is. You always see things, you know, how long it delayed by the time that it took the light to get to you. Well, in ordinary life, that's nothing. But in astronomical distances, turns out the light from stars that you can go out and see at night was emitted 10 years ago or 100 years ago, or in some cases 1,000 years ago. So you're seeing 1,000 light years away. That's the unit we use. But this distance was more like 1,000,000 light years away. So it was an astonishing fact that the universe was a whole lot bigger, and that was discovered just about 100 years ago. And it was using this idea that Henrietta Leavitt had unearthed. And so here's a diagram, a very famous diagram. We call it the Hubble diagram. Hubble, being a modest guy, called it figure 1. And it tells you about how fast away the galaxy is receding from us. That was the thing that Schleifer had been measuring. And how far away it is, down here, the distance, which is what Hubble was measuring. And you can see it's a pretty bad relation, but as you go farther away, the galaxies are moving away from us faster. Uh-oh, what the heck is that? It means that the universe is stretching out in all directions. Here's a diagram that I like to show in my classes. This is what I call the egocentric universe, in which you think you are at the center of things. The nearby things are moving away from you, and the more distant ones are moving away faster. And we've known about this for about 100 years, that we live in a universe that is stretching out in this interesting way. So when you look out into the universe, here's a picture from the Hubble Space Telescope, and you see galaxies. These are the systems of 100 billion stars, like the one that I showed you that Hubble had photographed. And some of them are nearby, and some of them are distant, and we can tell which are which from measuring this velocity and using that diagram I showed you a second ago. So that's pretty good. So we know we live in a universe that is expanding and that is stretching out in all directions. Well, if you remember, about 5 minutes ago, I said, well, Einstein invented this cosmological constant to make a static universe. And he gave up when he went to the Mount Wilson Observatory. Here's the Mount Wilson Observatory library. It still looks like this. Here's Hubble. He's being patted on the head by George Ellery Hale, who helped build the biggest telescope in the world 4 times. And here's the observatory director bursting with pride, standing next to Einstein. So the idea was that the universe was not static, but expanding. And so Einstein said, well, get rid of that cosmological constant. But I'm here to tell you that we have evidence now, 100 years later, that the universe is not only expanding, but expanding faster over time. And a very likely source of that is the same idea that Einstein hated 100 years ago. All right. And where's it come from? Where are we going and where we come from? This is the sort of question that kids ask from the back seat of a car. Alex is driving, there are kids in the back seat of the car. Where are we? When are we going to get there? And here's Georges Lemaitre. He was a Belgian priest and very well informed on all of this. And he realized that, well, if the universe is expanding now, then what if you ran the movie backwards? And there would be a time in the past when the universe is very hot and very dense. And as he said, the evolution of the world, he means the universe, the evolution of the world can be compared to a display of fireworks that has just ended. Some few red wisps, ashes, and smoke. Standing on a well-chilled cinder, the Earth, I guess, we can see the slow fading, and we try to recall the vanished brilliance of the origin of the worlds. Quite a poetic fellow. So we think there was a hot, dense time in the distant past, about 14 billion years ago, from current measurements, when the universe had this quality, and now we're looking at this vanished brilliance. Okay, So if you go to Washington and you go to the National Academy, there's a wonderful statue of Einstein. And here it is. And he has a kind of sheet here, which he has the various equations on, some of which you will recognize. Well, one of which you will recognize. This one you will recognize, E equals mc squared. This has something to do with the photoelectric effect. And this is the basic equation for general relativity. And the only point I am trying to make is, aside from the fact that I climbed up on the statue to take this picture for you, is that there's no lambda in that. The cosmological constant, no mention at the time they were making the statue. Okay, so let me tell you about something else, which is the way we have figured out how to measure the history of the expansion of the universe and to see that this lambda is actually back and now with evidence. So here's a picture taken with a cell phone in 1572 of Tycho Brahe and his castle. And he goes out there and he notices that in the constellation of Cassiopeia, which you might even be able to recognize, there was a new star. Gosh, what happens next? Oh, there's a circle. And everybody's pointing at it and getting excited. If you look at this thing, so that was 1572. If you look now, it's 450 years later. This is what you see. Well, you wouldn't see. This is what we measure. There's a exploded star. There's the shreds of an exploded star and a kind of a shock wave going out into the region around the star. So this is Tycho supernova of 1572. And it turns out that there are supernovae all the time in the universe. There hasn't been one that we've seen in our galaxy since 1604, but we've seen a lot of them in these other galaxies that have hundreds of billions of stars. So here's one. Here's a galaxy, not so different from our own, maybe a little dustier. And here's a star that is in that one single star in that galaxy, shining as brightly as a billion stars like the sun. So these are the key to figuring this story out, because you can figure out how bright those guys are if you can measure them. And so now we start to come a little closer to the story I was going to tell about Gordon Moore and about the foundation. So here, and about graduate work, really. So this fellow here, smiling and proudly holding one of the world's largest silicon detectors. It's a chip, a CCD, we call it. I like the things that are in digital cameras. This is a 0.24 megapixel camera. If you go buy a camera, you can't buy one that small anymore. But then this was the edge of technology, and you can see how proud he is. He was my advisor. And, for ARCs, the relation between an advisor and a student is really one of the most important things. A graduate school is a kind of apprenticeship, really, where you work with somebody and you learn the trade. Well, all right. So here's this itty bitty little detector. And here is Moore's law. Moore's law is about the way in which, not detectors, although it turns out it's also true for detectors, the number of transistors on a chip, say for a computer, increased with time. And Gordon Moore noticed that this was going pretty fast, that about every 18 months, it doubled. So here's a scale about how many transistors. Here's a scale about the years. Let's see, the first computer I bought was one of these. And, every 18 months, your computer becomes outdated because the chips are getting better. The price doesn't change, however. That's a very strange thing. Anyway, now the other point was that Gordon Moore, after whom the Moore Foundation is named, Gordon and Betty, his wife, was a founder of Intel. And as a result, his own personal wealth also doubled very rapidly over time. Here's $1 billion, and here's 5 billion. It's just about right. he became really ridiculously rich and started a philanthropic foundation, the Moore Foundation, to for the purposes that Gordon and Betty were interested in. I'll describe it a little more later, but being an extremely deeply generous person, he took this vast wealth and a significant fraction of it put into a philanthropic foundation for science, for conservation, for patient care, and for the Bay Area. But here's an example of Moore's law at work. He was holding, my advisor was holding this itty bitty little chip. Look at this, is the big thing. This is a more or less modern camera. And you can see how it makes people's eyes light up. This is John Tonry, one of my colleagues. And we are the beneficiaries of the same technology that works in computers for the detection of light with astronomical objects. Okay. Not only that, these are digital cameras. They measure the amount of light in each little picture element, the pixel. And you can put them into a computer and you can use that to find supernovae. So this is something that Alex Filippenko has done, and many other people have done since. So here's the idea. You take a picture tonight. Tonight is called Epoch 2 or Thursday. And you have some other picture in your library from maybe a couple of months ago, Epoch 1. And you can subtract the pictures because they're digital images. They're numbers in an array. You subtract them and look, this big fat galaxy goes away. Oh, that's good. All the other stars go away. The only thing that doesn't go away is here. This is the before and this is the after. It's hard to tell just from looking at it, but if you look at it really hard, you see this one's kind of elongated. And when you subtract out the first one, there's a dot left over. That's a new star. So the point is that the technology that Gordon helped develop is being used now to find distant supernovae through this imaging and subtracting approach. And I'll talk more about using the supernovae. Let me say just a word about what the world is made of. I talked about earth, air, fire, and water, and then I said, ha, 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 it's really the dark area around. And here's the clue to that, starting in about 1933, people were measuring the velocities of galaxies that were all in a cluster, ganged together more or less at the same place, and found they were moving with respect to one another, coming to and fro, where they're churning around as if they're orbiting some very dense thing, a lot of mass. And this fellow, Fritz Zwicky, shown here in a picture that his children don't like, had the idea that must be due to mass that we don't see, dark matter, Dunkelmatter. And he thought that these measurements showed that there was a lot more invisible matter than visible. Pretty daring idea in 1933, but we've made images since. This is an image with the Space Telescope of clusters of galaxies. So all these sort of yellow fuzzy things are galaxies. And look at these funny arcs, which are images of distant objects behind the cluster of galaxies that are warped by Einstein's effect of mass curving the space. And these images show that there's a lot more mass there than is represented by the stars. There's stuff there that is not visible, but whose effects we see. Okay. And just to carry the story forward into our own time, here's Vera Rubin, who I met and knew, measuring one of these spectra of a star, of a galaxy. And what she showed was that this idea that seemed so nutty in 1933, that galaxies have a lot more mass in invisible stuff than visible stuff is true for individual galaxies. So here's a galaxy, kind of a nearby one, where you can measure at different locations in the galaxy how fast the stuff is moving. Here's an image of that same galaxy done with radio waves that also shows what's coming and what's going. And the blue part is the part coming toward us. The red part, like that highway, is the part going away from us. And you can measure the rotation. You can figure out what the mass is. And it's way bigger. It's 10 times bigger than the mass that you get just from adding up all the stars. So that's the reason why people think a lot of the mass in the universe is invisible. The visible matter is tracing the location of the dark matter. But, it's a very strange thing. It's sort of like an iceberg, most of it is hidden. Most of the mass is not visible. The visible universe is tracing this invisible world. Well, if that doesn't sound crazy, wait till you see the next part. So what about the dark matter? If it's present in the universe, it's present in our galaxy, why haven't we been able to detect it? Astronomers knew in the 1600s that the speed of light was finite. I said it was a foot in a nanosecond. The trouble was, if you could only make a laboratory, some feet, yards, meters, whatever, large, the time from one side to the other was only a few billionths of a second. And, a pendulum clock is not too good for that. It took 150 years between the time there was an astronomical evidence for the speed of light till there was a real measurement in the laboratory. For the dark matter, well, 1933, Vera Rubin's work in the 60s and 70s and 80s, where's the direct detection? I don't know. Hasn't been found yet. There are many experiments being done right now to look for it. And, maybe it'll be next week. I don't know. But so far, we haven't found it yet. So maybe we're not looking in the right place. Anyway, we're pretty sure it's there. We don't know precisely what it is. It might be a subatomic particle, but we don't know for sure. Okay, now going back to the supernovas, exploding stars. Tycho saw one, and my graduate students have seen them. And we made a measurement of the velocity and distance for these special kind of supernovae. And look how nice it is. It's so much better than Hubble's diagram. Hubble's diagram, the one I showed you, would have fit in this little square down here in the corner. It was very nearby. The velocities were small. He did a good job, but that was just a little bit of the universe. This goes out to about a distance of 1 billion light years. Now, if you remember, I was talking kind of fast, but I said the age of the universe is about 14 billion years. So this is, sort of local. It's nearby. It's here and now. But the supernovae are bright enough that we can see them much farther out and see whether the expansion has been going at a constant rate or slowing down, as you would expect if the dark matter is the only part of the story, or doing something else. And this is the diagram from about 20 years ago, where this is our team, this is Saul Perlmutter's team in red. And what we measured was the velocity and distance of the supernovae that we found by techniques similar to the ones I showed. And it's kind of a mess up here, but I took out the 45-degree line. And what you can see is if the universe was slowing down due to gravity, dark matter, this dashed line is what you would see. And, that doesn't look right. If the universe was just coasting, it would be this horizontal line. And, well, an awful lot more points above than below. And if the universe was speeding up, speeding up, it would agree with the data better. And speeding up universe is one that has the cosmological constant or something like it, what we call the dark energy. Okay, so we believe that's true. Now there were two teams in the field. There's Saul, here's Adam, Brian Schmidt, who was my graduate student. Got him outweighed for sure. And this is what we call a full and frank exchange of views. But by 1998, it was pretty clear that we live in an accelerating universe. And the thing in the world that is making this happen is something like the cosmological constant that Einstein imagined. And Einstein looks pretty surprised, I can say. So what's the history of the universe? Well, it's kind of like a tug of war. Dark matter is trying to slow things down. Dark energy is trying to speed things up. And the way it works is that as the universe expands, the density of the dark matter goes down, the density goes down. The dark energy, if it's the cosmological constant, stays the same, so it's gonna win in the long run. And we're just at the moment where things are beginning to turn from slowing down to speeding up. Okay, so that was 20 years ago. People have done a lot more work. Instead of scrappy diagrams with 50 points on them, we've got these very well measured things, and they agree really well with evidence for cosmic acceleration. So here's our picture. I hate to talk about money, but on the back of the dollar bill, there's this diagram that is definitely, what is all this stuff? Anyway, there's this crazy eye thing, which is like the atoms in the world, the intelligence of the world. And there's dark energy and dark matter, and about 2/3 of the universe has to be in the form of the dark energy, and almost 1/3 in dark matter, and only a few percent in the atoms of the periodic table. So everything you have ever seen, everything you know, is just this little tiny part of the whole story of the universe. Okay. So time to shift gears. So here's a famous picture. This is in Venice. This is Galileo's telescope. And he's showing people the wonders of the universe. What Galileo said, all truths are easy to understand once they are discovered. The point is to discover them. And so we were very lucky. Alex and I and Adam Reese and Brian Schmidt, students, my students, we were very lucky. We're at the right moment. Here's Adam, and here's Brian. We're in Stockholm, where they received this Swedish prize, which is a good thing to get, for their contributions, my students' contributions to the discovery of cosmic acceleration. Okay, so you may think this is one weird story about the universe. So maybe some pictures will help, or art, actually. So, what do you see here? Well, you see snow on a mountain. You see the snow, but what's really giving the substance to it is the mountain. And the universe is like that too. What you see are the stars, but they're just a small fraction. The thing that's underneath it, that's the real mass of the universe, is invisible the way the mountains are invisible here. What about the dark energy? Well, we don't see the dark energy, but you don't see the wind either. What you see are the effects of the wind. So here an artist has beautifully depicted, the effect of trees swaying in the wind. So there's wind when you see the trees swaying. We know there's the dark energy because we see the cosmic expansion speeding up. Okay. And how long do we have to wait for this? I don't know. there ought to be a real laboratory measurement of the dark energy, something that really shows it's genuinely so, not just the astronomical argument, but it's really elusive and we don't really know how to do it. Okay, now let me talk about accelerating science. It's not so far away. So here's Gordon and Betty Moore, the founders of the Moore Foundation, where I work. And they founded this organization in 2000. So it's 20 years old. Next year, we'll be able to drink a black magic shimmering cocktail. And Gordon was one of the founders of Intel, and as I alluded, the founder, the author of Moore's Law. And they did very well, and they set this up. The endowment of the foundation today is about $8 billion. So it's one of the largest foundations in the US. They really helped us a lot with ways of thinking about what to do. Generally, we don't solicit proposals, although sometimes we do, but we used our staff, who are very knowledgeable, and advice from a very fine science advisory committee to kind of figure out what to do. But Gordon and Betty helped us make this little rubric for how to decide what to do. Is it important? If it's not important, why would you do it? Can we, the foundation, make an enduring difference? That's really a statement of modesty. That is, you know, we don't want to do stuff just because it's good. We want to do it because we're going to make it. The foundation is essential to making a difference. Gordon was a legendary advocate for measurement. And so in the foundation, like in his technical work, we emphasize the idea is, you know, can you measure what you're doing? The apocryphal story, which I can tell because Gordon told it about himself, is that Gordon, who's old but healthy, but someday he will be called to the pearly gates. And when he is, St. Peter will say, you know, come on in, Gordon. But Gordon will say, no, I'd like to go to hell for a comparison sample. So he's somebody who really cared about properly controlled measurements. And we try to do it. Of course, it's not a very precise business in the philanthropy world. And then in our little world, we have what we call a portfolio effect. That is, does one grant kind of help us understand what's going on in the case of another? And Gordon and Betty have been very helpful to us. They wrote down in a little booklet, which they called the founder's intent, their intent. The foundation is supposed to endure in perpetuity. Well, phooey, that's a legal concept, but astronomers know that that's not right. The sun is going to swell up and become a red giant. The earth is going to be incinerated. It's not perpetuity, but anyway, without limit of time. But what they wrote, which was very helpful, is our support of science stems from Gordon's background and interests. Expanding knowledge is both intellectually satisfying and often of practical value. Very helpful. Both areas can be accelerated, I knew he would use that word, by carefully targeted private funding. And really, I went to your website, and this is much like ARCS. This is the idea that if you pay attention and put private money in the right place, you really can help the progress of science. So let me just close by saying at the Moore Foundation, we have some big projects like the 30-meter telescope, which we hope to build. And we invest in people the way you do. We've just announced, and we're going to launch a thing called the Moore Investigators in Experimental Physics, which is going to be faculty members at a certain stage that we support. But it's got the same idea as what you do. The same idea is you find those people who really have the drive, who really are going to contribute, and you support them with adequate funds. Okay, so let me stop. you know, on your website, or when people talk, or when people go to talk, they testify in Congress, which, you know, it's an experience. People talk about science for technology or defense or medicine. You know, people want to be rich, we want to be safe, well, we want to be immortal. Okay, well, just long lived. But honestly, the kind of science I've been describing tonight is something different, because you could be all those things, rich and safe and immortal and bored. But the ideas are so interesting. The question of what's the universe made of? Where did we come from? Where are we going? All of these things really have a grip on people's imagination. And I've seen that many times in the classes I teach or talks that I give. So I really think that in addition to those practical and very good things that science can yield, an important part of science is the joy of finding out how the world works. So thank you very much. It's my pleasure to speak to you tonight.
That has been awesome. My goodness. So, Linda, would you like to make a couple comments? I know that just to wrap up, I have another admission here. I do that too. But I will take chat questions or hand raise. You can go down and raise your hand, and I will call on you. Would you like to just make a couple comments to Robert, Bob?
Well, first of all, Bob, thank you very, very much. I've always been curious. I don't know if I've asked you this before, but what lured you from Harvard to the West Coast? Because clearly you took a grand leap from the science that you were doing
Yeah.
to the Foundation science program. But did they come and lure you in the middle of the coldest Boston winter and tell you how beautiful it was in California? What made it all? What started it all? How are we lucky enough to have you in California?
Well, you've put your finger on the meteorological phenomenon. The winter of 2014 was the most awful ever winter. Anybody who knows, that was the biggest snow winter anybody had ever seen. And, you know, I grew up in New England. I was not a wimp, but man, we didn't know where to put the snow. And it came every week. So when, and my wife, Jane, you know, is kind of she's thoughtful. And she said, you know, Bobby, for spring break, which is March, we're going to go to Santa Barbara. I said, oh, great, you know, because I'd been on sabbatical in Santa Barbara and stuff. So she rented a place in Santa Barbara and we went out there. And at that time, they were recruiting for somebody to be the head of science at the Moore Foundation. And the president of the Moore Foundation is Harvey Feinberg, who had been the provost at Harvard. And, you know, how you don't really know the provost unless you're in trouble or something. But, you know, I kind of knew him socially. And then he went to the National Academy and I would see him like once a year and he was very nice. And anyway, Harvey, so I knew him. And Harvey said, well, why don't you come up and talk about it? And here's what he said. He said, you know, I said, well, you know, I'm doing this fabulous work, although, of course, my students won the Nobel Prize, not me. And he said, yes, yes, he said, but you have climbed that mountain, he said. We have other mountains here. Why don't you, you know, try something new? And I thought, yes, and in a warmer place where you don't have to shovel so much snow. So I did it. And Portola Valley is, of course, a beautiful place and where we live. And that's been great. The only thing is, when there were all those fires last year, you know, we got in the car and drove to this house in Maine that we'd had from the years at Harvard. And So we're sort of cowering from COVID, but it's pretty good. So we'll come back, is what I'm saying, once we each have 2 shots in our arms plus a little time to make the antibodies.
But you are still doing your research.
Yeah, so I made a deal. My deal was 20% of my time. And, a reasonable person would say, oh, 20% of your time, take 1 day every week or 2 months out of the year. Actually, the way I do it is I have like 12 seconds out of every minute I spend on, my astronomical work. So anyway, yes, I am still doing some, but mostly by proxy. You get to a point where making it possible for other people to do their work that becomes your work. And that is, that's where I am now. And so that's what I'm trying to do, is do things wisely with this vast amount of money that Gordon has generated, to make it possible for really good people to be able to do their work. We're small compared to federal funding. And, ARCS is small compared to other things, but it's not vanishing. And it makes a difference when you focus it carefully on really good people to help them. And they know it, and they appreciate it, and we measure it the best we can.
I have a million questions, but I certainly don't want to stop anybody else. Nancy, are you in charge of chat?
Linda, what was the first question you would like to pose?
Oh, well, no, don't leave it up to me. I feel like I've done
Okay.
I've had all the fun.
We have a couple really good questions in chat here.
Okay, I'm ready.
One of them is, what is the relationship between gravity and dark energy?
Yeah, that's a very good question. It's probably right to think of the dark energy as an aspect of gravity, that in addition to the pulling together, slowing down part, there's another aspect to the way gravity acts, that is this repulsive, really, part, the part that makes things fly apart. So we're not used to that at all. You throw a ball up and the ball comes down. If you threw a ball up and it, accelerated up further, we would just fall over in astonishment. But it could be that the big story for gravity includes this other aspect, which is so subtle we don't see it on the small distances we're used to. But on the cosmic scale, it makes all the difference. So your common sense about things is not always right, because we've grown up in a place where, you can catch a ball and you can see a ball and you kind of know what it's going to do. You know what the trajectory is going to be under a gravitational field. That's how you play baseball. But on the cosmic scale, these more subtle forces, which are not noticeable even in the solar system or local phenomena, can be the dominant thing. Well, apparently are the dominant thing. So it's a very subtle sort of story, in which there's another aspect of gravity that we really don't know much about, and it reveals a kind of ignorance that we have about gravity on the cosmic scale that I find kind of exciting, because it means there's really something important to be discovered that we just haven't sorted out yet. There's something missing right at the heart of physics. So you could be a little discouraged. You could say, well, we've made up all this stuff. We made up the dark energy, we made up the dark matter, but to account for the things we see. But I think the evidence is really good. There's more than just the supernova data. And we really do live in an accelerating universe, and the explanation for that has to come from understanding gravity more deeply.
Okay. So I put a question in. What is the obstacle to understanding dark matter more?
Yeah, very good question, of course. Well, here's the story. We're sure it's not anything from the periodic table. So it's not any element or any particle that you know about from ordinary experience. It's got to be something else because it doesn't interact with those things. And we know how those things interact. It only interacts, as far as we know, by gravity. Well, could there be such a thing? Yes, there can be. There can be subatomic particles that we haven't discovered yet, but that, could be prevalent in the universe from the hot Big Bang that have enough mass to be the dark matter. Now, if that's true, then they ought to be present in the Milky Way, and we're in the Milky Way. So an experiment on Earth ought to be able to detect these things if they interact at all. And the idea is, well, maybe they're weakly interacting particles. There are 4 forces, and the weakest of them is called the weak force. And maybe they are weakly interacting particles, sort of like neutrinos, that, but not yet discovered, but more massive. And you can build an experiment on that hypothesis. If there's a weakly interacting particle, every once in a while it will bang off a nucleus. And you can put many nuclei in a vat and look for the recoils. And people are doing that. There's a big experiment being in a mine in South Dakota, underground, so it gets away from cosmic rays, where they're looking for this to happen once a month in a ton of xenon. Well, that's pretty subtle work, and you have to do an incredibly good job of blocking out all the other signals. But there have been a whole series of experiments of this character carried out by incredibly dedicated and clever people. So far, they haven't seen it. Well, does that mean it doesn't exist? No, we're sure it exists. It just means it's not that kind of particle, or, they haven't done a sensitive enough measurement. The problem is it could be some other kind of particle that's much lighter and harder to detect. So I think it's wise now, after a couple of decades of looking for the most likely kind of particle, these weakly interacting massive particles called WIMPs.
Wimp?
Yeah, well, they were in contrast to the machos. We make up these funny names. That maybe it is some of these other kinds of particles, the very light ones. There are, in particle physics, there are things that people are pretty sure exist, but that have never been seen, the axions. Maybe that's something that our other neighbor, Helen Quinn, was involved in inventing that. I don't mean to wave my hands too much, but the number of possibilities is so large that even if you don't see something in the place where you look for it, it could be that it's really a particle of a different kind. So I think this story is definitely incomplete. And until we have a laboratory experiment that shows it's really real, there's going to be a lot of uncertainty. But I think the paths to do it are pretty well defined. And at the Moore Foundation, I've helped fund a couple of things, searches for dark matter.
I have a question.
Good. Go ahead.
Yeah, my question is twofold. One is I asked if he could speculate. Do we think there's other life on the other planets that might be similar to ours? And also, my belief was Einstein felt that the laws that we encounter were very physical and correct. And so what does that mean about religion? I would be curious to his speculation on that.
Okay. Well, let's start with life in the universe. One thing that we've found is that most stars have planets around them. And we didn't know that 30 years ago. So that's pretty good work. And that means there are many opportunities for places to have the right temperature, maybe water, where, at least in the case of Earth, that's where life has arisen. So I think the optimists say, well, it could be pretty common. And you can see that this is a really important area of science. We should really work on this and do our best to try to find out if that's true. One way to do that I can think of is to look at the planets that are around other stars and see what their atmospheres look like. You know, in the case of Earth, the fact that we have oxygen in the atmosphere is entirely due to the action of living things that breathe in carbon dioxide, exhale, trees that exhale, or plants that exhale oxygen. So if we saw that in the atmosphere of another planet around another star, that would be a good clue. So life, if you get a bunch of biologists together and you ask them to define life, they have kind of a hard time. But I think the possibility that there could be life elsewhere in the universe and the number of opportunities there are for it kind of puts the question on the table anyway, that there could very well be life in other places. Now, is it intelligent life? Do they want to communicate with us? Okay, those are other questions. Then you ask the question about religion. Well, for Einstein, the idea of it's really beauty of physics and the wonder that it evokes in us. For him, I think, although he was a, ethnic Jew and he was kind of knew about that culture, he wasn't really all that interested in it. He was more interested in the other idea of beauty and wonder and the exhilaration that we all get from knowing that we're in and part of this fantastic universe. So, whether you call that a religious feeling or something else, I don't know. But I think most people who are not, practicing religious people who are scientists, nevertheless, share that sense of awe, that sense of wonder, and the joy of living in a universe that is so intriguing and full of wonder.
I'd like to bring this back home, and that is we have 6 universities that ARCS provides scholarships to in various disciplines in STEM. Can you tell us which among these 6, and I think you know what they are most likely to contribute to this science?
Now, you better tell me which ones you've got.
Stanford, San Francisco State, UC Santa Cruz, UC San Francisco, UC Berkeley, and UC Davis.
What a good bunch of places.
Yeah.
Well, I'll tell you this, in the UC system, the observatories were kind of an autonomous thing for a while. Berkeley, of course, was the flagship, but the Lick Observatory up above San Jose is an old thing, and another unit really of the University of California. It goes right straight to the president. And then in the about 1970 or so, Santa Cruz became the site for the headquarters of the of the observatories. But every one of the places that you named, to my knowledge, has a really good program. Davis has built up their program. UCSF has astronomy, less than the others because it just doesn't have as long a program. But Stanford, for a long time, was the best university that didn't have an astronomy department. And now it still doesn't have an astronomy department, but it has the Kavli Institute, and the physics department has got a very strong astrophysics group. So every one of the ones you Stanford, in fact, does have a very big and active dark matter experiment, the Xenon one, or Lux, I think they call it now, which is active, and they're looking, and by golly, they could be the ones to find it if anybody does. And Berkeley, of course, has a very strong program. So all of them have strengths in these areas, and any of them could be, the source of a great discovery.
Okay. Well, Bob, on behalf of ARCS, well, actually, I'm not the one that's going to say good night, but Deborah, would you like to please unmute, and would you please thank Bob after I've just tried to steal your lines? Bob, thank you very much.
It's been my pleasure. This is a really great group. You're doing a wonderful thing. I had, when I was one of my colleagues, I remember, got an ARCS scholarship, and it's just been, it was a really big boost to their graduate program. So you're doing a really good thing. People appreciate it very much.
Maybe we could team up with you. We've got good stuff going on.
Yeah, good idea.
So first of all, I want to say thank you to Bob. This was amazing. And I also want to thank Linda Millard for making this possible, for making the connection. Do you have any other neighbors that maybe you could China?
She does. She has a neighbor who won the Nobel Prize. She has a neighbor who invented the axion. She's got some neighbors.
Well, perfect. And then
There's nobody like Bob.
Well, I would be inclined to agree. I want to tell you about our next science activities, which is April 8th. And this is about climate change. And we have Daniel Swain, who is an ARCS alum. And we have Noah Diefenbach, who is also an ARCS alum. And the good news is they're not on this call, because to follow you, Bob, I don't know. Anyway, they are going to talk about climate change, and we welcome all of you to join us for that. I think this has been a very special evening, and thank you to all of you who attended. So have a great evening.
Thank you, Bob.
Thank you. See you. It won't be too long, Linda.
Okay, come home soon.
Yeah. Well, when we'll bring the new dog.
Oh, ooh, good.
Thank you, Bob.
Bye.
Yeah, okay.
It was great, Bob. Thank you so much. It was so interesting. So
well, good. It wasn't a detailed analysis of science funding in the United States, but I thought this would be more fun.
Well, it's all Greek to most of us, but the more we hear it, the more we get it. And it's very exciting work. Super.
Yeah, I think the idea that we can actually understand some of this is really quite amazing. And we need the next generation to work on it, and you are really helping.
Well, thank you. We all work hard at it.
Yeah.
Okay, ladies. Lovely. Thank you, everybody.
All right. Thank you. Bye-bye.
We'll see you back in California, Bob. I hope to meet you in person.
Yeah. I'll be happy to do it. Bye-bye.
Bye, everybody.
Hi, everybody. Excellent.
Great job, Nancy.